In this question, we want to return a special MST. So we want to return not just the minimum spanning tree, but a special minimum spanning tree where, if you can look at the output, it says the minimum width spanning tree in which the nodes of U are leaves. So first off, we need to know what it means for a node or for a minimum spanning tree to have nodes which are leaves. When an MST has nodes which are leaves, it means that its vertices has only degree 1. And the number of degree is a number of edges. So that means that its vertices has only one edge. Let's look at the example given in the question. If we were to draw it, to show nodes and leaves, the MST would look like this. We want to start from 1, and 1 goes down to 4. 1 also goes down to 2. Then 2 goes down to 3, and that's it. Yeah, that's it. So we see that at the vertex, let's call 1 the vertex. At the vertex 1, we have degree 2 degrees. It has 2 children. Then we have this as slave, this as slave. But when we look at a special example, I just want to illustrate this with a diagram so that we get what we're talking about. We start from 1, which is the first node. It has one edge which points to 4. Then we make 2 another node, because when we join it now, we now have the vertex 1 having degree 2. So we have 2 another node going down, connecting with 3. And because we want this to be a 3, we can then join it at the leaves. I hope this makes sense. So let's look at a general algorithm for solving this kind of problem. So first of all, you want to find your MSTs using any algorithm you find easier. Let's say we use our Prim's algorithm. So we want to start by using our Prim's algorithm. You start by using Prim's algorithm. Let's say Prim's algorithm for finding MST. So once we find the MST, we've gotten the second diagram. So the B part, what do we do? So we want to check if any vertex in U, we want to check if any vertex in U, let's say if any vertices in U are not leaves, and we start from the cheapest, just like we started in the diagram. We start from the cheapest. We want to check if any vertices in U are not leaves in the MST. If all of them are leaves, then this is our answer. The correct MST is our solution. If not, we move on to C. And if any vertex in U is not a leaf, we want to find edges that connect U to the tree that has maximum width. We keep this and remove the costlier edge. It's just like what we did when we drew the second part. We started from the cheapest. We started from the vertex, the first vertex 1. That's the vertex with the cheapest edges. Then we drew the cheapest edge, we connected the cheapest edge, and we left out the costlier edge, which is the one connecting 1 to 2. So for C, we want to check if any vertex is not a leaf. We want to find the edges weight, number one. Connect the minimum weight, and then leave out the costliest. Then we leave out the costliest. So we are going to repeat this until we have all leaves. So we want to repeat until all so we just repeat this for all nodes or for all vertices until all of them are leaves, and by the time we get all leaves, we come to the last two leaves, the ones at the very bottom. Let's say we've been working and we have something like this. We come to the ones at the very bottom and then connect them to make our MST. I hope this made sense. If you did like this video, remember to subscribe, like, comment, share, and I'll see you on the next one, which will be an introduction of a new topic.